The problem in the lab here is everything like I have to finish the unit 1. Suppose if I go there. You guys are listening? You guys are seeing my screen?
Yes, ma'am.
Okay. Okay. See, if I finish this only, you will be able to understand how you can draw a structure. You know, drawing using the mouse and keeping one dot is different. But what are the force field? How to represent a structure, you will understand only after I finish this. Okay. And the next is, after we model the structure, we have to work out the energetic level, the conformation, and the structural relaxation of the molecule. This after this unit 2. Okay. Then once I finish these two only, I can go to unit 3, where I am teaching the molecular dynamic simulations. Okay. So this is like, this will take time. But during this time, simultaneously, we train you for the lab. You know what will be the lab? That is to some softwares which can handle the modeling of 552. Yeah. So there is a modeling. Suppose, you know, everybody is those that the RCSB website, right? How many of you don't know? We have learned it, right? PDB website, right?
Yes, ma'am.
Okay. So the main part is like, here you can download whatever is the PDB ID, you can put it and you can download. It will give you the format, PDB format. But once you download, you should be able to view the structure. You should be able to understand the fragments of the structure in the order. If it is a nucleic acid, then you should worry about the ATGC pairing and the number of things, everything. If it is a protein, then you will be able to understand the sequence of every amino acids and which domain and everything. Okay. So the first phase of the syllabus, we really ask you to really understand the structural input given in the PDB file. Okay. So the PDB file format, which I already explained in the data bank. Okay. The visualization of a molecule is like you play in a software or in any, what is that? Here we have given Pymol and Chimera. Okay. This is, see, Pymol is one software and the Chimera is one software. For rough use and everything, you can use Pymol. For a manuscript submission with a clear thing and more features, you can use Chimera. But the thing is that the visualization, that is, you download the PDB file here, you display the structure, maybe in line or some other CPK model or ball and stick model, whatever it is. Then you have to understand the basic interaction, whether it's a hydrogen bonding within the continuous units, basic units, or amino acids or the nucleic acids, or it is like probably one amino acid. Suppose if I say amino acid 1 is interacting with amino acid 10 in a remote way, you know, that is the type of understanding. And the B factor, okay, I explained this, the B factor during that PDB. Remember, Debye wallet parameter that explains the thermal destabilization of the region, protein region, because all the regions from the top to bottom, from N terminal to C terminal to N terminal, we cannot crystallize if that structure has loop regions, because loop regions are always flexible. Okay. But when the same molecule, when it comes in complex, interacting with other molecule, the loop may get adopt a secondary structure either by the counter ions or by the water mediated interaction or by any incoming ligands and whatever it is. Okay. So this unit 1, the first lab session, you have to, okay, do this. This has to come in practice. I think in the first lab probably Mahesh used to handle it. Mahesh had some fever issue. That's what Shilpa came. And I suppose she must have introduced you the Pymol. Okay. Is it so, Shilpa?
Yes, ma'am.
Okay. So when this Pymol comes, it is like you have to download this in your system. You have to install this in your system, and you have to open that graphics page. Then you have to download, see the structure, and get to know. See, you write down everything one by one. What is this? What is this? If not, okay, if Shilpa is not, when she is, her internet connection or whatever is goes wrong, and if you are not able to follow, no problem. The problem is you have to go, you can get your understanding from tutorial 1. For every software, you have a beginning protocol is given in this one. See, I learned this molecular dynamic system by online with the books, with the softwares available, and now, see, from 2002, I'm learning, and now we are able to come. So, nothing is like, very speculative like a C program or Oracle program or whatever. It is like you have to download your structure in the graphics window. You have to see, okay, what is this? Oh, all atom representation. What is this? Yes, so side chain. All these things, you have to use by hand. Okay. One time, if they say you stop, Shilpa. Okay, madam, you stop. I will write, then you can proceed. So it is more of the homework for the student that you have to do it. Now we are discussing this lab through online. Definitely it has its own drawback, but we have to overcome this. Okay. So if anywhere, in any place, if you are lost, you ask Shilpa or Mahesh and keep to wait for some time. You note down and ask them and get the answer, write down. Then you can proceed. And Shilpa, when you are taking in the remote thing, you speak very, very slowly.
Okay.
Whatever you speak, you type it in the chat box.
Okay.
Okay. Whatever you speak, you type it in the chat box.
Okay.
See, it is very, very important that every student understand this topic and leaves, because for another 6 to 10 months, I suppose the same online scenario will exist, and we have to somehow train them as equally as of offline. Okay, so you should have some patience. Even I should have some patience. I'm taking very slow only. Last semester compared to last semester, this semester I'm taking very slow. Students, how do you feel about my class? Are you able to get all the things when I'm teaching in the theory side?
Yes, ma'am.
Ma'am, theory it is clear.
What is that, ma? Theory?
In theory, ma'am, all is clear, ma'am.
Okay, fine. So, Shilpa, you go slowly. You make sure that every line delivered by you is taken care of. Made the students understand all your content. Then proceed. Okay.
Okay.
Okay. And you tell Mahesh also. Mahesh, are you online?
No, ma'am.
I think he is also not okay. Yeah. Okay. So a little more, we have to be little more slow. We have to be, if it is a 9 hours lecture, we have to go with more than three, another, whatever lectures we want, we have to. So somehow we will do it. Okay. Shilpa?
Yes, ma'am.
Okay. So every day, what I see that if you are taking one lab today, you immediately assign that write-up of all the students immediately after the lab, and 2 days before the previous lab, they should submit you the pendant.
Okay. Okay.
Okay.
Okay.
Okay. Then only you should proceed next. Okay. And students, it is your responsibility to put extra effort in the internet and get your doubt cleared. When you are online with her, you can clear your doubt. If something is missing, you can also go to the online and get it. Okay. This is not the toughest part. This is another kind of play. Wait, somebody's mic, please mute it. Please mute it. Please mute it. Shilpa. Okay. Okay, so students, you have to be, this is not a one-side delivery, and you have to equally participate and put your effort and come up with a complete understanding of the idea. Is that correct? Okay, so I think from the next class onwards, I will also try to be online because last class I wanted, but somehow, we have to take care of your class, we have to take care of administrative work, we have to take care of our research, and everything is in our pipeline. So we are running behind time. Okay, so please cope up, and anything comes, we can discuss, no problem. Is that fine now? Yeah, just a minute. I will come and join. Okay, sorry guys, got some job. Uh, so what we were talking? So anything related to your tutorial, something you please update yourself and get the doubt cleared, and then and there you write the note, and you have to finish it. Is there any other issue on the lab? Because I forgot to log in before your lab session and explain all these things. So anything, any doubt or anything from your side, students? No sound? Okay then. Shilpa, you can log out, Shilpa. I will continue the class. Okay. So, students,
Yes, ma'am.
so anything, any other issues? Okay, so we go to the theory. Why everybody is off now immediately?
Okay, ma'am.
Yes, ma'am.
Hmm? Okay. So in the last class, what we finished? Okay, what we finished in the last class? No sound? Huh? No sound?
Ma'am, the last class, I didn't understand the last part.
Okay. What is the last part? You didn't understand.
Ma'am, I actually couldn't get it. You were telling about the energy or something, and I just zoned out. I couldn't uh, get what you were. Yes, something similar diagram you drew in the jam.
Here.
Uh, no, that the U shape, the V shape diagram. You were
This
telling
one.
something. Yes, yes, ma'am.
So I was telling like the energy, if you plot the energy with respect to the displacement of any particle moving, I mean any particle showing a equilibrium positional change. Okay. Okay. Here we are considering there is no friction, nothing, no disturbance from the environment. So your body, if it's keep on moving, it will keep on moving. Okay, it's a Newton's law. That is the moment of inertia, right? As long as you are not disturbing the body, that will keep on its own position, either it's a resting position or in a moving position, right?
Yes, ma'am.
So here your body is your what is that? Now we have taken the simple pendulum motion and the pendulum is moving, right? What happens? It is a simple harmonic motion from the equilibrium position. Suppose you see that this is the fixed point and the pendulum is moving. The pendulum will come this side. The pendulum will come this side. So what happens? It will keep on like this. Understand? So from the equilibrium geometry, every increment the displacement will accumulate energy because now it is entering from the resting state. It has only the potential energy. When it starts moving, it will slowly increase its kinetic energy. So during this phase, the kinetic energy and the potential energy will be remaining same. Here, if you say your total energy is only the potential energy, here your total energy is potential energy, or the contribution will be there, but kinetic energy will dominate this event. Okay. So what happens is, now the higher energy, lower energy, it is not like a continuous pencil drawing. Okay. It is, you have to now, instead of imagine this as a line, now you have to imagine this as a energy frame. What the energy frame? You cannot, as a Cartesian coordinate, you cannot simply say 1, 2, 3, 4. Okay, but there is a space of energy. This space of energy is governed by the quantum energy. The quantum energy is described in terms of the Planck's constant. Okay, so every energy level, see, like how we are stepping in the staircase to the first floor, your increment will be a step. Here, the step size is h cross omega. So, energy level, first energy level, when we say this is the principal quantum number, n is equal to 0, n is equal to 1, n is equal to 2, 3, 4, everything. So, even if the n is equal to 0, you don't expect that the energy will be 0 because the by default, the basic energy level difference, this is the inertia of the body, will be there. So half h cross omega will start, then every increment plus h cross omega will go. Suppose this is 1 means. So I take this half outside and I take this n is equal to 1. So n plus half into h cross omega, because every increment is a half h cross omega. And every line you have your own increment half is there. So general way you are writing n plus half h cross omega. What is the problem in this? You want me to write this? I will take a Jamboard. Where is the Jamboard? Today also recording is not coming. Start a new board. Choose from the driver. Is it from my driver? I think I have not saved it anywhere. I think this I can take. Okay. Possibilities there. Share with. Share with no. All I want. How do I? Only why it is sharing only with 4. Styling sharing on. Oh, this is anyone at the center for no. Okay, those who are getting, you please share within yourself. I will just cut now. Okay. So I think class I was talking about. I think. Okay. Okay, this picture, right? You Narayana. If don't okay. So this picture you are talking about, you are getting as what is this? You don't understand.
Yes, ma'am.
So what is that? Now you are able to follow what I say.
Ma'am,
See, yeah, 1 minute. Huh? See, sorry. the energy is equal to N plus of H cross omega. How? This is N H cross omega plus of H cross omega. This is every intermediate. So this N takes the value N is equal to 0, 1, 2, 3, etc. So if you put 0, this goes 0. So when N is equal to 0, that is in the first principal quantum number, the energy is equal to of H cross omega. Correct? When N is equal to 1, then E is equal to H cross omega plus of H cross omega, that is 3 by 2 H cross omega. So this is E for the energy level, N is equal to 1. Similarly, E for the energy level 2, it is 5 by 2 H cross omega. So it goes on like that. Any problem now?
No, ma'am. I got it.
Okay. See, I'm not good in writing this one. You know, I cannot, I don't like to share this also, but I have to. Until I find, buy some, what is that, digital board and something, you have to bear with this. And suppose if you know any good, what is that, e-board or something, you suggest me, I'll buy. And I'm using a laptop, so I can afford and buy it, but probably I want to check the pricing also. Okay. When it is available free, let us use this until now. Okay.
Okay, ma'am.
Okay, ma. But don't show it to others, huh? So it is like, I think when my daughter was in LKG also, she didn't write like this. Huh?
No, ma'am.
Okay. So now coming back to this. Okay. So the scenario now is, okay, now I'm coming there again. Okay, I'll close this. So the scenario is, how do I go next? Shrutika, அன்னைக்கு என்ன சொன்ன? Next. Yes, it comes. Okay, perfect. So coming back to this, whatever we are, okay, I can use any color. Okay, fine. So now the problem is, there's a table point. From there, we have a pendulum. Okay, the pendulum is attached to the string. The string is attached to the wall. Nowhere the string is free or the ball is free. I mean, the pendulum is free. It is in a bound form. Correct? Okay. So, suppose for me, if I take methane, okay, I put C and I draw a tetrahedron geometry. I put hydrogen. I put hydrogen. Okay. So what I should do, if I want to model this, okay, what I can do, I have to first consider the C with H. This is a bonded system. Sorry. This is a bonded system where your C is fixed with some charge nature and your hydrogen is connected via a string and it is moving. This hydrogen will not move like this, like a pendulum. But what will happen? The hydrogen may move little along it, or it will compress, or it can bend, or whatever. Within some region, allowed region, the hydrogen will move. You all agree?
Yes, ma'am.
Okay. So this is an example of a bound form, and you can apply a model of C connect to the H. But here another important point is that the C has a 4 valency. You are working with only 1 valency. Then you have to simplify the ignored part as a unified charge C and do this. This is the beginning. I'm just telling. This state I will modify it later, but for your understanding, I'm just telling. So the hydrogen what is absent now, what we are not considering now, will be put 0 or will be wiped out, but we will put some essential correction in the C so that the H is also the influence or the geometrical representation of the H is also indirectly represented in the electrostatic way. So clearly speaking, we are taking one C which unitedly has the representation of 3 hydrogen, but it is not shown in the graph, and we are simply taking one model of this. So what we have to do? We have to take one model, one CH, another CH, another CH, another CH. Then we have to make this C representation properly. Then you combine this, and this will become a model of CH4. Okay. So this is how the determination or the representation, structural representation of the methane happened. To begin with, the people studied like that. But now the system is very clear. They have learned everything. So if you say somebody who is working in this field, they can directly put the CH4 as a bonded system and represent what is the charge of this, what is the charge of this, what is the charge, what is the angle, what is the bond length, and everything, the 3-dimensional representation they will take. Let us keep this as an example and worry only about the pendulum and the similar representation of the CH in a bonded nature. Okay, you agree?
Yes,
You
ma'am.
all agree? Now I am talking about another one. Suppose I have a CH4, okay, and some agent, some chemical agent is coming. What happens? One hydrogen is removed, okay, and it is bringing some other atom. Let us not go with the chemical status, but I will consider only one stage where the C has only 3 bonds, the other bond is cleaved, correct? The intermediate state, I'm just thinking. I have not come to the product side. I have not entering into the initial, what is the reactant side. I'm only working on some intermediate state where one bond is cleaved. That is, this is in the not bound form. Okay. That is, this is a free form. Okay. So, in such case, such cases can come into a catalytic reaction. A catalytic reaction in biology or anywhere in chemistry always means that a bond breaking is there, or there is some atoms interaction which are not directly bonded, either by covalent or by ionic or by coordination, is also coming into interaction. This is a type of interaction, hydrogen bond. So we have a necessity to represent a non-bound state, a free interacting atom state. Understand? So in that case, if I use, okay, if I use this is a model for always a bonded system, but I want to also have a system where you are able to talk about bond dissociation, that is bond breaking, that is involved in the catalytic reaction. You understand?
Yes, ma'am.
So in such scenario, we are thinking about little correction in this one. Okay. So what does it mean? What does it mean? Okay. I have a particle A. I mean one atom A, and it is interacting with B. For example, this is O2. It has one peculiar bond. Okay, so this is the nature. Let as it is in the natural state, that is the stable state, that is the global minimum state. So it has its own energy, its own bond energy, it was bond and length and everything. I keep this. Okay, I am putting one energy scale. Okay, this is the distance r. So this is the distance r. Okay, so what I say that I keep. Okay, this is the molecule. Okay, what is this? I keep this molecule A. I want to make, sorry, this is the atom A, and I want to bring the atom B to interact with the A and form a bond. In the beginning, my B is here. This is, I say, at a distance of infinity. Okay, what I am doing? I am bringing this closer to the A. To a particular time, that will slowly start feeling this one. So what happens? There is attraction. What means? This is energy in the direction. So what will happen? It will try to stabilize the interaction between A and B. So there is a decrease in the energy. Why there is a decrease in energy? If I take atom A, if I take atom B, there is an electronic cloud outside, inside a positive. Electronic cloud outside, inside a positive. This positive will interact with the electrons. This positive will interact with the electrons. There is a significant attraction between these two. So there's a stabilization of energy. Not 100%. To some extent, I'm talking. Okay. So what happened? There's a slowly, there's attraction, 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 and one particular point, this is done. What is this is done? Where this A and B can form a equilibrium geometry like this, it will stay. Okay, this is the equilibrium position. But now you imagine, can you bring, suppose if I have A here and I have an electronic cloud outside and a charge here. Can I bring the same atom B like this? This electronic cloud will not allow a very perfect collision or contact between another atom because this is the electronic cloud, this is a negative charge, correct? And also the positive charge of the nucleus will not allow the closest to very close to itself because there is a demand for a reasonably separate space between this and this. That is what we are having one bond, correct? So this is the stable state, and if you still bring this closer, what will happen? The cloud will get fused in, which is in real, it will not happen. So it is an unexpected, unwanted energy. The energy will try to the atoms beyond this state. Beyond the state, the atoms will try to repel each other because it cannot form a fused or like an adhesive state. So what happens? The energy, I am putting one line here until this is the attraction. And from here, there is a repulsion between this and go straight. Okay? Go straight. My straight line is also not straight. So this region is formed by A and B repulsion, and this region formed by A and B attraction. You guys are following?
Yes, ma'am.
Okay. So now I am bringing another thing that we have studied. What is that? Harmonic oscillator. Okay, the harmonic oscillator can only talk about the bond, but the curve what I explain now only can talk about bond breaking. So this is the bond formation. This is the okay. I think this should come like this. 1 minute. Maybe I should be very careful and making this like this. Okay, so harmonic oscillator is talking about that bond breaking, and okay, and this will come like, little more wide. Okay, go like this. Okay, so this will get increased because you are coming closer to this displacement. So now we are representing, this is the one which is the real potential that is talking about non-bonding interaction. Okay, so this non-bonding interaction is explained by a potential called, this is derived by a scientist called Morse. Okay, so the scientist Morse derived or modified the harmonic potential in such a way, saying that it is also accounting the bond breaking event in the non-bonded level. This is like coming to closer level. This is the bonded level. So all these things, with all these iterations, what happens? We are bringing a Morse potential like this. But here, the separation of the energy level is not equal. This is, in the beginning, it is wide. When it goes up, it is very close. This is characterized. Why it is characterized means this goes with the spectroscopy explanation. Let us not worry about it. But you can simply take it as sense that harmonic energy separation is equal. The Morse potential energy separation is not equal. So this is the equation. What is this equation? You have see that. Now we have an energy. Okay, we are starting from nu is equal to 0 to the last level, to the infinite level. That is the dissociation energy, because this is in the state, it is the dissociated. Okay, so where every time, this energy dissociation, equilibrium energy, now we can calculate from this point. This is your equilibrium. And now using this equation, you can go with the exponential decay, which is taking a relative positional difference. That is R, you are taking a difference with RE, equilibrium position. And this is the exponential square function that is explaining the Morse potential, that talks about the attraction as well as the repulsion of the energy. Now let us consider the same Morse potential. Oh, this is 230, yeah. Okay. Okay. Now, so you can have the same Morse potential in a different elongated or up-to-date form, that is the Lennard-Jones potential. Attraction part, we have a repulsion part. So the Lennard-Jones, we say this is the 612 potential, Lennard-Jones 612 potential. Shruti, half an hour. Oh. Valli and help it to go. Lennard-Jones potential, 12-6 potential contain two adjustable parameters. One is that sigma by r power 12. The other one is sigma by r power 6. Okay. So by an attractive part is always power 6, because that is also, the nature is also characterized. And this 12 power is also a repulsive power. So we have two terms talking about the non-bonding interaction between two atoms. That is, this is by the attraction, this is by all over, you are having one potential which is able to talk about the non-bonding interactions between the atoms. Okay, so now with this I conclude. Don't worry about all these things. This truncation will come in some other class, not this class. So today the message from my class is how our harmonic oscillator is explained and where it fails, and that is how the harmonic oscillator fails to explain the bond breaking event. So the Morse potential is designed in order such a way that we can also talk about bond breaking event or other non-bonded interaction systems. So it's a very, very important question. Define harmonic oscillator and explain, define Morse potential and explain, give us the analysis of harmonic oscillator and the Morse potential and explain its application. So something, every question has such question in the semester exam or in the internal. So one of the very important concept that you should keep in mind. Is that fine?
Yes, ma'am.
Yes,
Yes.
ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay. Okay. No more questions. Any questions for me?